NASA has finally unveiled a fresh set of high-resolution images captured by the Hubble Space Telescope. And what they reveal about the interstellar visitor 3I Atlas is unlike anything astronomers expected to see. What was once thought to be just another comet passing through our solar system now appears far more structured, far more dynamic, and far more mysterious. For the first time, we are seeing details that raise deeper questions about how this object behaves and possibly where it came from. The images were captured during a rare geometric alignment that briefly placed the Sun, Earth, and 3I Atlas nearly along a single line. In astronomical terms, such alignments are fleeting and highly valuable. From Earth's vantage point, the object appeared almost fully illuminated, similar to the way the moon looks brightest at full phase. When sunlight strikes an object from directly behind the observer, surface and dust structures can become far more pronounced. Subtle variations in brightness sharpen. Fine streams of material stand out against the darkness of space. In those alignment images, the Hubble Space Telescope resolved a bright halo extending nearly 100,000 kilometers toward the Sun. That scale alone is extraordinary, a glowing envelope stretching nearly 10 times the diameter of Earth. But what truly captured scientific attention was not simply the size of the coma, it was the structure within it. 3 distinct jets emerged from the inner region surrounding the nucleus. They were not randomly scattered nor loosely clustered. Instead, they appeared spaced at roughly 120 degrees from one another, forming an almost geometric triangular configuration. In cometary science, jets typically originate from localized vents where volatile ices sublimate under solar heating. These vents are often irregularly distributed across fractured terrain. The resulting plumes can appear chaotic or uneven. Yet here, the spacing seemed balanced, almost evenly partitioning the circle around the nucleus. One jet appeared brighter and more dominant, while the other 2 were somewhat fainter, possibly due to orientation relative to Earth or differences in activity levels. Even so, the 3-point symmetry remained unmistakable. It gave the object a structured appearance, not smooth, not uniform, but organized. During this alignment, a visual effect known as an anti-tail appeared to project nearly toward Earth. Anti-tails are well understood perspective phenomena that occur when dust trails align with the observer's line of sight. In this case, however, the effect amplified the sense that 3I Atlas was momentarily presenting its activity head-on. The halo glowed intensely. The jets stood out in relief. The configuration looked deliberate. The physics alone can produce remarkable order under the right conditions. But structure was only the beginning. Continued monitoring revealed that the jet system is not fixed in place. The dominant jet oscillates with a steady rhythm of approximately 7.2 hours. This periodic motion was not a visual illusion, but a measurable shift in orientation across sequential observations. At the same time, photometric measurements showed that the object's total brightness rises and falls with nearly the same period, fluctuating by close to 30%. For a cometary body, that level of brightness variation is significant. A simple rotating sphere with evenly distributed activity would produce more modest changes. A 30% swing suggests that active regions are either highly concentrated or that the geometry of dust scattering is changing in a coordinated way. Further analysis detected additional periodic signals embedded within the jet behavior. The 2 secondary jets showed oscillations on timescales of roughly 2.9 hours and 4.3 hours. When combined, these shorter cycles correspond closely to the primary 7.2-hour rhythm. This pattern hints at a complex rotational state rather than independent bursts of activity. Instead of chaotic venting, the jets appear to participate in a synchronized mechanical system. The leading interpretation involves precession or nutation, a subtle wobble in the object's rotation axis. If the nucleus is not spinning in a perfectly stable orientation, its axis may trace a small circular path over time. Imagine a spinning top that is slightly off balance. As it rotates, its axis slowly sweeps around. Any features attached to that axis, such as jets anchored to specific regions, would appear to oscillate in a predictable cadence. If 3I Atlas is undergoing such motion, the jets effectively map its internal mass distribution. Precession implies asymmetry. A perfectly uniform sphere would not wobble this way. There must be uneven mass concentration, irregular internal structure, or sustained torque generated by uneven outgassing. Comets are known to change spin states when jets act like natural thrusters, gradually altering rotation periods and orientations. What makes 3I Atlas unusual is the apparent stability of its triple symmetry combined with measurable axial wobble. The brightness fluctuations reinforce that interpretation. As the axis tilts, the angle at which sunlight scatters off dust particles shifts relative to Earth. Certain orientations enhance forward scattering, making the object appear brighter. Other orientations reduce it. In this way, the object modulates its own visibility through motion, a rhythmic brightening and dimming linked to its rotational dynamics. Yet even this intricate behavior does not fully explain why 3I Atlas has drawn such intense scrutiny. It has always been peculiar. The first anomaly was its trajectory. 3I Atlas follows a hyperbolic path, confirming that it is not gravitationally bound to the Sun. Its speed and incoming direction indicate that it originated beyond our solar system. That alone makes it historically rare. Only the third confirmed interstellar object ever observed passing through our planetary neighborhood. Its orbital plane lies surprisingly close to the plane in which the planets orbit the Sun. While not impossible, such alignment is statistically uncommon. The rare Sun-Earth alignment that allowed full-phase imaging was itself an unusual geometric coincidence. Then came the high-resolution revelation of the symmetric triple jet structure. The pronounced anti-solar jet appeared unusually directed and sustained. The brightness modulation amplitude suggested a compact but energetically active region. The 7.2-hour wobble introduced a precise clock-like rhythm. The subharmonic periodicities at 2.9 and 4.3 hours reinforced the sense of coordinated dynamics rather than randomness. Evidence of precession implied internal imbalance. The 100,000-kilometer halo demonstrated robust dust production despite the object's interstellar origin. Across multiple observational sessions, the triple symmetry persisted. The jet's orientation shifts appeared structured rather than erratic. The object passed through regions of planetary influence without obvious fragmentation or disruption. Its peak visibility coincided with favorable observational geometry. Activity appeared confined to specific regions rather than dispersed widely across the nucleus. When considered collectively, these characteristics form a pattern that is difficult to dismiss as trivial. These interconnected peculiarities were organized into a catalog of 18 anomalies by Harvard astrophysicist Avi Loeb, who argued that while each feature has a plausible natural explanation, the accumulation deserves continued investigation. Taken individually, the alignment imaging, the rotational wobble, and the anomaly catalog each represent separate lines of inquiry. Together, they define 3I Atlas as an object that resists easy categorization. Whether future observations ultimately reinforce conventional explanations or reveal additional layers of complexity, one fact remains: 3I Atlas has transformed from a faint point of light into one of the most closely examined interstellar visitors in modern astronomy. Attention is now shifting toward a pivotal moment on March 16, when 3I Atlas will make an exceptionally close pass by Jupiter. The projected distance is approximately 53.6 million kilometers, about 0.35 astronomical units. On an interplanetary scale that may sound vast, but in gravitational terms it is strikingly intimate. That distance lies almost exactly at Jupiter's Hill radius, roughly 53.5 million kilometers, the boundary where the planet's gravity begins to dominate over the Sun's influence. In other words, 3I Atlas will skim the very edge of Jupiter's gravitational sphere of control. The Hill radius represents a delicate balance point in celestial mechanics. Outside it, the Sun governs an object's motion. Inside it, Jupiter can meaningfully redirect trajectories, alter spin states, or subtly reshape dust environments. Passing so close to that boundary raises important scientific questions. Even a modest gravitational nudge could slightly adjust the comet's velocity vector, refine its outbound trajectory, or perturb its rotational dynamics. For an object already displaying a measurable wobble and coordinated jet activity, the encounter becomes an opportunity to test how stable that behavior truly is. If the triple jet symmetry is rooted in internal structure, a gravitational torque from Jupiter could amplify or dampen the wobble. If the rotation state is already marginally unstable, the planet's influence might trigger a detectable shift in the 7.2-hour cycle. Astronomers will be watching closely for even subtle changes in brightness modulation or jet orientation before and after the flyby. A stable continuation would strengthen the case for an internally robust configuration. A deviation, however slight, could reveal hidden sensitivities in the object's mass distribution. The encounter also presents a rare observational opportunity. Researchers, including Harvard astrophysicist Avi Loeb, have proposed that NASA's Juno spacecraft, currently orbiting Jupiter, could attempt to observe 3I Atlas during its passage. While Juno was designed primarily to study Jupiter's atmosphere and magnetic environment, its vantage point near the planet could offer unique imaging geometry. Observations from within Jupiter's gravitational domain might provide perspectives unavailable from Earth-based or Earth-orbiting telescopes. Such measurements would not only refine trajectory calculations but could also test whether the comet's activity responds measurably to tidal forces. Even weak gravitational stresses can influence loosely bound cometary material. If dust production increases or jet patterns fluctuate during or after closest approach, scientists would gain direct evidence of how external forces interact with this interstellar body. Interstellar travelers are rare enough. One that brushes the boundary of Jupiter's gravitational dominion, while exhibiting structured jet symmetry and measurable rotational wobble, is rarer still. Whether the passage leaves detectable changes or confirms the stability of its unusual features, March 16 will mark a defining chapter in the study of 3I Atlas, a moment when celestial mechanics, observational opportunity, and cosmic coincidence converge.